Welcome to Hartman Math. Today we're going to look at analyzing the graph of a function. Before we get into that, a little warm up on work we've been doing with functions. Go ahead and pause the video here, work through problems 1, 2, and 3. All right, number 1, we are looking for an answer of 3 minus the square root of the quantity n minus 1, as n minus 3 replaces the x. So we would get inside the root n minus 3 plus 2. The minus 3 and the plus 2 become the minus 1, and that's as far as we can go. Number 2, h of negative 4 is 18, as negative 4 satisfies this part of the criteria. So we're going to use this part here. Negative 4 squared plus the 2 becomes the 18. H of negative 2 is 6. Negative 2 also satisfies this criteria, so we're going to use this part of the definition. Negative 2 squared plus 2 is 6. And h of 10 is negative 5, as 10 is greater than negative 2, so it satisfies the second criteria, so we're going to use the second definition. And lastly, the difference quotient. With that, we should get a final answer of 2x plus h. Go through all of that. Also, remember to try to stipulate that h cannot equal 0. All right, so example number 1 and 1.5, analyzing graphs of functions. We're looking at the graph of the function right here with just some different kind of points highlighted there, and we're going to be asked for the domain first, and we're going to think, okay, what are all the possible x coordinates, or conversely think, how far does this graph move from left to right, that kind of thing. We can see that from left to right it starts here at negative 1, and clearly there's a close point there, and then it goes all the way over to here to positive 6, but an open point, so that our domain in interval notation is bracket negative 1 because of the close point, comma 6. Doesn't quite get to 6 because of the open point right there. Part B, the range, all of the possible y coordinates. We may want to think of how low does our function go to how high does our function go. If we think of it that way from bottom to top, how low it goes is negative 5. Again, close point. I think we're going to go bracket negative 5, comma, how high does it go? This point's not really that important anymore because we do go higher. This is as high as we go, and the y-coordinate there is 3, and it does reach that value, so that is going to be a bracket. And then evaluating the function f of negative 1, kind of thinking in terms of f of x. Well, the x-coordinate is negative 1, so go over there, find where the x-coordinate's negative 1. F of is the y value, so we're just looking for the y value, and that would be negative 5. F of 4, according to this point, is 3. F of 6, according to this, well, it's not 2, because it is an open point. There is no point there, so it is undefined. There is no defined value in f of 6. 6 is not in the domain. That's why we had the parentheses there, so we don't get a value there. All right, checkpoint. Think of the function f of x equals the square root of x minus 4. And think of what the domain and the range would be. Pause the video here until you can come up with a response. All right, it might help us to think and create a graph for this if we think in terms of a parent function, the square root of x, which starts at the origin, kind of bends this way. And then if we think in terms of translations, which we'll also re-emphasize later in the course, this would mean shift right 4. So we could think of our graph starting here at 4, kind of going like that. So according to that graph, the domain, bracket 4, comma, infinity, going to right forever, and the range, it starts at 0 and goes up forever. Another way algebraically we could have thought about this, and we talked about this previously, is we're, in terms of a real number graph here, we're only allowed to take the square root of non-negative things, positives and 0. So in terms of domain, we could have thought x minus 4 has to be greater than or equal to 0. And if we solve that, that's what we're going to get for the domain. All right. Determining, talked about this in a previous lesson, what is a function? Well, if we're looking at the graph, and that's what we're doing today, analyzing graphs of functions, if we're looking at the graph, we can perform the vertical line test along the graph to determine if our relation represents a function. Zeros of a function, again, if we're looking at the graph, anywhere we have an x-intercept, well, that value, that x value, so it's going to be just a number, is a 0 of the function. Okay? And we also looked at that in a previous lesson as well. Any value of x for which we substitute into the function and we get an answer of 0. They're very connected. So zeros of a function are connected to the x-intercepts of its graph. Find the zeros of the function f of x equals 3x squared plus 4x minus 7. We're going to go through this algebraically. We can set the function equal to 0 as the first step. This being a quadratic function, we have different strategies to solving quadratic functions. Factoring is one of those strategies. So we can factor this into 3x plus 7 and x minus 1 equals 0. And once it's factored, we can use the zero product property, split these apart, set these both equal to 0 separately. 3x plus 7 equals 0, x minus 1 equals 0. We've had a lot of experience in previous courses with that, so we kind of want to just jump to the next step. We can get the solutions from there. There's our setup. And solving that two-step equation, we can get x equals negative 7/3, or from over here, x equals positive 1. Those would be the zeros of the function. And connecting back, if we were to graph, although it's not asking us to, these would be where x-intercepts would be found. Negative 7/3, comma 0, 1, comma 0. Checkpoint, go ahead and find the zeros of the function g of x. Go ahead and pause the video here until you come up with the zeros of the function. All right, so a little bit more complicated here, where we have now here a rational expression, a fraction with x's on top and bottom. In this case, we know we can't divide by 0, but zeros are really just going to come from the numerator. So if we set the whole thing equal to 0, we can multiply both sides by x plus 5, in which case 0 times x plus 5 is still going to be 0. So as we can see, the denominator doesn't really matter in this type of problem. If we solve the numerator now as an equation, it becomes a square root method problem. It doesn't have an x term, it has x squared but no x, so the square root method is a good option for us here. To get x squared by itself, add 7 to both sides, and then square root both sides. Do not forget the positive and negative values that you get there, so those would be our zeros. Probably box that answer right there. Those are the final answers. Another thing about functions that we're going to look at in terms of their graphs and analyzing increasing and decreasing functions. Book definitions, as you can kind of read through here, they really get to be very, very complicated, and the language, if you can understand it, great. If when it says x1 is less than x2 implies that f of x1 is less than f of x2, if you don't quite understand what that's trying to get at, that's definitely okay here. If we kind of simplify it in terms of a graph, if you look from left to right, and you must be traveling along the graph from left to right, increasing means it's going up. Decreasing means it's going down. Constant means it's horizontal or flat in an interval. And when we respond to these, we always are going to be wanting to talk about domain intervals. So we're going to be given the x-coordinates. It goes up from here to here, and that's going to be our interval. Okay. So our example, something like this, it's decreasing here as we go from here to here, traveling to the right. It's going down, so it would be decreasing from -2 to 0, thinking of x-coordinates. It's constant from 0 to 2, and it's increasing from 2 to 4. Now, the way that we're going to do this is you're always going to respond on an increasing, decreasing, and constant question in interval notation with parentheses every single time, because at -2, it's actually after -2 that it starts to go down. It's in transition here at 0 between decreasing and constant. So that's why we're always going to use parentheses and never brackets when we discuss increasing, decreasing, and constant. So taking a look at an existing function here, f of x equals, it's a complicated function there, -x times the square root of x plus 6. But here's what it looks like. See if we can determine open intervals. That's what I was talking about with the parentheses there, when it's increasing, decreasing, or constant. So using this idea of travel along the graph going from left to right. So function looks like this. So from here to here, it's going up. And it's, again, always x-coordinates. So from -6 to here, that's where it stops going up, and that's at -4. Open interval, so we're going to use parentheses. Starts at -6, stops at -4, that's where it's going up. Decreasing, well, it's going down, 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 down. So it's, for the rest of it, it's going to go down starting at -4. And notice here, it doesn't have an end point. It's just going to keep going. So that's going to mean it's going to head to the right forever. So from -4 to infinity, also in parentheses. There are no places where it's flat or horizontal or constant. So we could say something like none. Pause the video here, a checkpoint. We're given the graph of a function here. See if you can determine the open intervals. Remember, think domain intervals, x-coordinates. Where is it increasing, decreasing, and constant? Pause here until you have a response. It is increasing here. Even though it's pointing left, we don't want to think of it that way. We want to travel always going from left to right. It's going up here from -infinity, stops going up at 0. Think of x-coordinate. It is constant from 0 to this x-coordinate, from right there to there, 0 to 4, and then from 4, it's going to go down forever, so starting at 4 and going towards infinity there. Next thing about functions and their graphs that we're going to look at is when is a function odd or even, and this connects back to previous discussion on the symmetry of a graph. And the two symmetries that are really going to be important here are symmetric about the y-axis and the point symmetry about the origin. So as it goes through, a function is going to be even if, and here's the algebraic test here, if f of the opposite of x is equal to f of regular x. And an even graph, that's going to have the symmetry from a graph perspective in the y-axis. An odd function, algebraically, f of -x will equal the opposite of f of x. So notice that we're always starting our check with f of -x. And if we do this algebraically to test for even or odd, we will always start with f of negative x, or g of negative x, or q of negative x, and that's going to always be our start. And then it's going to be even if we finish with the original function. It's going to be odd if we finish with the opposite of the original function. Maybe one of those doesn't happen, and it would just be neither. It's not going to be even or odd. So if we look at a graph, and again we go back to the symmetry, our parabola here is symmetric about the y-axis, and that's going to make it an even function. And an odd function will be symmetric about the origin, meaning if we put our pencil or finger right here on the origin and we just spin the graph halfway around, half a rotation, 180 degrees, if it looks exactly the same as the way it started, like f of x equals x to the third, that would be an odd function. So the way that we would determine this algebraically, is it even or odd? Again, we go back to that algebraic definition. We would start with f of negative x. That's our start. Always start with f of negative x. So now we're going to go into the function. We're going to replace every x with negative x. Definitely want to use the parentheses. So we get 3 times negative x plus 4 times negative x cubed. Now we're going to see if we can simplify this. So 3 times negative x is negative 3x. If we cube negative x, a negative x times a negative x times a negative x, well, since we have an odd number of negatives being multiplied, that's also going to be negative. So we have negative 3x, and then a positive times a negative becomes negative 4x cubed, and that is not the original function. So I'm pretty sure that this is not going to be an even function. So if I'm trying to determine if it's odd, I will always want to take a negative and factor it out to see. So I'm going to factor out a negative just to test to see if it's odd. If I do that, factor out the negative, I would get 3x plus 4x cubed. I'm going to notice, hey, that's my original function. So to satisfy that actual definition, I want to go all the way, and I want to replace this with f of x. So I'm going to finish with, don't stop here, I'm going to finish with, hey, that is the opposite of f of x. And I've satisfied the definition. I started here, I finished here, and that's the definition of an odd function, and that's my conclusion, and this is my evidence that I started with f of x and I finished with negative f of x and I got odd. If I started with f of negative x and I got just plain old f of x, I got this, that would be enough. I would say equals f of x, and I would conclude that it's even. So try that out on these. Pause the video here as you go through the checkpoint, checking g of x, checking h of x. Remember to start with g of negative x, start with h of negative x, substitute in, see what you can come for a conclusion. All right, g of negative x, we replace the x with negative x, and it's cubed. And again, if we're cubing a negative, we're going to get a negative x cubed minus 1. That is not the original function, so I'm probably not thinking even. If I want to test odd, I'm going to factor out the negative. I get x cubed plus 1, but that's also not the original. It's not the opposite of the original, as these don't match. So that's neither. It wasn't the original function g of x. It wasn't the opposite of g of x. That's a neither situation. With h of x, h of negative x is equal to negative x squared plus the 1. If we square negative x, a negative x times a negative x, well, negative times a negative is a positive. So we would get positive x squared there plus 1. And we'll notice, hey, that's my original function. So I can replace this with h of x, and by the definition, h of negative x is the original function h of x. I can conclude even at that point. Thanks for joining me. We'll see you next time.